So one of the important things that I talked about in those videos is that when you have reactions, they fall into the four categories of uh, Sn2, Sn1, E2, and E1. And so really the whole trick of this is to figure out which of these reactions is going to happen. And essentially what we have for the most part is that you're either going to have a nucleophile for your substitution reactions, or you're going to have a base for your elimination reactions. And so you just have to kind of figure out what it's going to be. So the first thing you need to figure out is that when you have some type of carbon with a leaving group, typically a halogen, you just need to figure out what this substitution of this carbon is, meaning, is it a methyl, a primary, a secondary, or a tertiary? So we could have methyl, primary, secondary, and tertiary. And the reason why we do this is that this is the most important thing to tell what reaction is happening, because if you know what's happening, if you know what type of carbon has your leaving group, you can tell what type of reaction is possible. It limits what type of reactions you can have. So as I write here, Sn1, Sn2, E1, and E2. So you have to just figure out, does the carbon that has my halogen or leaving group, is it a methyl like CH3 chlorine, or is it a primary, a secondary, tertiary? Sn2 prefers methyl, primary, and secondary. You cannot have a tertiary carbon with Sn2 reaction. Sn1's the other way. It prefers tertiary, secondary, but you can't have primary and you can't have a methyl. For E2, E2 prefers tertiary, secondary, and then primary. Can't have a methyl. And E1 is just like Sn1, or tertiary, secondary, can't have a primary, can't have a methyl group. So if you see a methyl group, Gwen, like CH3Br, what's the only reaction that can happen?
Sn2.
Sn2. Yep. So you just kind of have to figure out, you have to kind of look at everything and say, all right, what's happening? Is there a preferred, is it a nucleophile? Is it a base? Is it a strong nucleophile? Is it a strong base? And this right here is just the most important thing. If you can get past this step, this limits you. The only one that you have to watch out for, and this is true just because most chemistry professors will make their question secondary because everything's in play. But if you do get something else like this, you can start making selection choices. Okay, we can talk about Zaitsev and Hoffman a little bit, but just this right here is what you want to figure out. So can I erase this? Are you guys good? Okay, so the next thing is that when we talk about your nucleophiles and bases, strong nucleophiles are typically going to have negative charges just like our bases, right? So you think now you just run into the issue though. What's the difference between nucleophilicity and basicity? So essentially, what makes a good nucleophile and what makes a good base? They're both going to be electron rich, so you kind of can't tell that. So negative charges are going to be, yeah, that looks like it could be either one, right? So nucleophiles are electron rich, good bases are typically electron rich. Good nucleophiles are typically going to be small. Usually your better nucleophiles are small so that they can get in and do Sn2 attacks. If you remember, when you do the Sn2, your size of your nucleophile and the carbon, like it's a methyl, primary, secondary, whatever, that's what limits it. Base can be any size. And the question that someone asked was, well, what about like Zaitsev versus Hoffman? And that's going to come into play. So really, if it's small and it's got a negative charge, you're going to lean towards nucleophile most of the time. If it's any size, and it can be a base. So you just have to pay attention to what's happening. I think, Mag, you're about to ask a question.
Yeah. So for I'm like, I can't do it today. Nucleophiles, would you say that if you had a base, don't like both have like negative charges?
Yeah.
Or can possibly have like
But you
negative
can have good
charges?
nucleophiles that are neutral, and you can have good bases. Your bases typically have to be negative, but your nucleophiles can be neutral.
Okay, so you just need electrons, basically, like lone pairs.
Yeah, that's why you need to be electron rich. You
Okay,
need to have
yeah.
some level of electron density.
Right. Okay.
Right? So polarity, yeah, that does play into it, but that also, like, it's really hard to tell. But here is the easiest way to remember. There are only 3 common bases that are strong bases and strong nucleophiles. So if you remember this, this will help save you a lot of time. The only 3 bases and good nucleophiles: hydroxide, OH minus, methoxide, OCH3 minus. You can also see it as OMe minus, and typically you'll have like a metal with it, like a sodium or a potassium or something like that. And then ethoxide. So basically the deprotonated forms of ethanol and methanol. And that can also be written as OET. These are the only 3 reagents that can go to either Sn2 or E2. So if it's any other reagent that has an O minus, it's going to typically be a base. So how do you tell if you have something like hydroxide, methoxide? So say like you have a common, like here, I'm going to draw this as an example. So if you have something like this, and I use, say, sodium hydroxide, do you guys have a prediction as to which way this reaction is going to go?
The OH will replace the Br.
Is it going to be an E2 or an Sn2? Which reaction do you think is favored here?
E2?
Sn2.
Sn2.
E2. So as a reminder, E2 prefers tertiary more than secondary, more than primary. Sn2 prefers methyl more than primary, more than secondary. So if you have a secondary one, it is going to favor E2. So if you had something like hydroxide, methoxide, ethoxide, this favors E2. Mags, do you remember what the other thing I said that can help you favor Sn2? The one thing that we can do to our reaction conditions? So if you're ever
sp3.
Well, they have to be sp3, right? Yeah, but there's also something we can do to our reaction, like when you run the reaction. High temperatures will always favor elimination reactions. So if you have over your reaction arrow something like 100 degrees Celsius or 50 degrees Celsius or something like that, like a temperature that's higher than room temperature, that's always going to favor E2. I don't know if Dr. Dewis is going to have that on the exam, like those types of questions, but if you ever see a reaction and you're not sure if it's Sn2 or E2 or Sn1 or E1, anytime you raise the temperature, you favor the elimination reaction. All right, so what about this one? And I did the same reaction condition, so I did NaOH. Would this favor E2 or Sn2?
Sn2?
I'm going to say Sn2.
It's Sn2 because it's a primary, and primary is more favorable than it is for E2. So this is just how you pay attention to those. Oh, it should be lowercase a. It's just you watch out for that. Those are basic principles, and they will stick to you. So if you remember those basic ideas as we go through and do it, that makes sense. So we can talk about the Zaitsev versus Hoffman conditions, and then we can hop into the practice exam just so we have this little Do you guys have any other questions about this stuff besides Zaitsev and Hoffman? Or are you good? Okay.
Wait, I'm still
Oh, okay.
okay. I'm good. Thank you.
You're welcome.
Oh wait, I actually have a really quick question.
Mhm.
So the bottom reaction, even though that's primary, right?
Mhm.
Okay, so even though it's primary, if that were to have a higher temperature, would it then favor E2?
If you push it enough, yeah. If you really, really push it enough, so then it would probably be like a 50-50 split, but no teacher would ever do that.
Okay.
So, all right. Good question, though. So now when we talk about elimination reactions, and remember, what's the product that we always form in an elimination reaction?
H, like H and a base, and then the halogen.
Nope, that's side products. What's the main product that we always form in an elimination reaction? It's an E reaction. We form alkenes. In E reactions, we form alkenes. You always form a double bond in elimination. That's how I remember that. But for an example here, say this is our actually, I'm going to try this again, and I'm going to draw this in the middle. Say that we have our substrate here, like this, and we have our leaving group, which we're going to say is a bromine. All right, so now we have hydrogen here. We have a hydrogen here. Right, there's 3 there, but I'm just drawing one of them. And then we have hydrogens here, like that. So we have, so the carbon with our leaving group, you know what that's called?
Alpha carbon.
It's our alpha carbon. It is the carbon that has our leaving group. So then we look at carbons adjacent to that. So this is our alpha carbon, but then we look at the carbons adjacent to that. Actually, I'm gonna change color here because that might make life a little bit easier. These are adjacent to my alpha carbons, and these are what we call beta carbons, right? And so we look at our beta carbons. So E2 reactions are also called beta elimination reactions. That's the fancy name for these. In a beta elimination reaction, we are going to take a proton from a beta carbon. That is going to form a double bond. And in that process, we are going to kick off our leaving group, right? So the question now becomes, which I think Matthew was, the heart of his question here was, well, what if we have, say, a small svelte base like sodium hydroxide versus a very large robust base like potassium tert butoxide. So I think you probably have seen these in a lot of way, right? Potassium tert butoxide. So if I was actually, I'll just draw this out so you know what I'm talking about. So potassium tert butoxide, there's a lot of ways that you can think about it, but it is essentially an O- on a tert butyl group, right? And so then our hydroxide is just the OH minus. So what's the difference going between these 2 bases? What's the main difference?
One's a lot bigger than the other one.
Yeah. We're going to introduce an idea of a small base and a bulky base. Mag is a small person. I am a bulky person. The same idea. So this is what we introduced the idea of Zaitsev and Hoffman. So I know that you guys love your history. He said, lying to himself. But do you guys have any idea what this means in terms of reactions? I need to grab my phone real quick. Think about what Zeiss and Hoffman are like. Okay, so Zaitsev and Hoffman are just named after the scientists who discovered these reactions. And the idea is that when the scientists did these reactions, essentially what they found out is that Zaitsev did these experiments the same time that Hoffman was doing experiments. So while Zaitsev was doing this experiment, Zaitsev was doing elimination reactions and was like doing a lot of like really cool, just like a lot of elimination experiments, did a lot of fundamental research into this. And what he discovered was that as Zaitsev was doing these reactions, is that the type of base started playing into what product you form. And so in a Zaitsev elimination, essentially what happened is that when Zaitsev did these eliminations, he used small bases. And so what the end all result is that if you use a small base like this here, like hydroxide or something like that, if it's a base that doesn't have an isopropyl group or a terpetal group, like a small base, you will take the proton from a beta carbon that is more substituted. So these two are secondary, and this one here is a primary. So the Zaitsev rule is if you have a small base, you will take the proton from the more substituted carbon. Also, a way to think about it is, I'm going to erase this over here and just draw this again with a little more detail. If I draw this again, right, so we have our Br. We have two hydrogens here, and then we have this C, and this has 3 hydrogens. So the Zaitsev rule says you will take a proton from the more substituted carbon, secondary versus primary, or you will take it from the carbon with fewer hydrogens. There's 2 there, 3 there. You can make that distinction either way, either if you can tell that it's a secondary versus a primary, or if you can tell that the carbon has fewer hydrogens. Does that make sense? You look a little unsure, Max.
So since you have 2 hydrogens versus 3, you would pick the one with 2.
Yep.
For the
Zaitsev, for the smaller base, OH minus, yep. So this is what Zaitsev discovered, that when he did his reactions, when you did the whole reaction, I'm going to erase this here, is that when you did this whole reaction, the major product, if you used OH or another small base, would always be that the double bond formed would be between the more substituted, oh, that is bad. The more substituted form would always be between the more substituted carbon, right? And there's a lot of reasons for this thermodynamically and kinetically, but we don't have to get into that unless Dr. Dewis really wanted to learn it. Has she told you the specifics of why this happens? Some professors care, some professors don't. So if she doesn't care, we're not going to care either, right? But now when we use the bulky bases, whenever we have something bulky, what is the major concern? And it starts with S. Two words, SH.
The steric hindrance.
Steric hindrance, right? Size becomes an issue at this point because if you get too large of a base, you can't attack more substituted carbons. So when you have bulky bases now, Hoffman, who was a German scientist at this time, was working on the same thing. Zaitsev was a Russian, and he did this stuff in his labs, and he discovered that E2 with small bases gives you the more substituted. Zaitsev, on the other hand, discovered, because he was using things like tert butoxide or isopropylamide or other stuff like that, diisopropylamide, is that if you use a big base, you are going to take the proton from the less substituted carbon or the carbon with more hydrogens. So then your product here would be, the double bond would go to the less substituted carbon like that. So that's the difference between Zaitsev and Hofmann. The Zaitsev is preferred with small bases. Hofmann's preferred with bulky bases. So if your base has the term tert-butyl or isopropyl or isopropyl, any isopropyl or tert-butyl groups will give you the Hofmann rule. If it doesn't have it, assume the Zaitsev rule. Questions? Oh, I see something in the chat. Yep, this is similar, just like to Markovnikov and anti-Markovnikov. So essentially, Markovnikov and so Zaitsev and Hofmann refer to elimination reactions. It tells you which proton you take. So Gwen, if I had a Zaitsev elimination, which color protons would I take in this one?
The pink ones, if that makes sense, or the
hydrogens are colored uniquely. So if I had a Zaitsev.
Oh, like the hydrogens themselves.
Yeah, which hydrogen would I take? The blue, the purple, or the green for a Zaitsev? Zaitsev is our smaller ones.
Could it be a blue or a green?
Yep, it would be blue or green. These are going to be your Zaitsev. You take it from the more substituted carbon. So then your Hofmann would be from the less substituted. All right. Zaitsev is always preferred unless you have a bulky base. So can I erase this? Okay. So now, as with all good things, let us do a practice reaction. Sorry, I had to think in my head. Give me the major and minor products of this reaction. Give you guys like another 30 seconds. And yes, Gwen, it was nice to go to Maryland. So
I love Maryland. I'm like, Annapolis is one of my favorite cities ever. It's so beautiful.
it's a nice place. I think I'll probably go visit more as I live here. So I definitely go back to Annapolis because that's a nice place. And
Next time you go, try the Federal House. It's so good.
I think you're like the second person to tell me that, so that's definitely on my list.
Really? Yeah, their crab chowder is really good. And it's fresh because it's like right there.
So first, let's take a think about our base. So first off, is this going to act as a base or a nucleophile, or can it do both?
It can be both.
Yep, NaOCH3. Remember, this is one of our three that can be either E2 or Sn2, right? So we know that E2 and Sn2 is possible because this is going to be either a strong nucleophile or a strong base. So that's fine, right? Now, what was the first thing I told you to look at whenever you are doing this type of problem? Find your halogen or leaving group and look at the carbon that it's attached to. What type of carbon is that? What's its substitution? Methyl, primary, secondary, tertiary. How many carbons is it attached to?
Sorry.
3, so it is a tertiary.
Okay.
So since it's a tertiary, is it Sn2 or E2? Yep, it cannot be Sn2, right? Sn2 cannot happen on a tertiary carbon, so it must be E2. So it is going to be an elimination. So now we know that this OCH3 is going to act as my base. We know this is a strong base. Now the next question is this going to be a Zaitsev elimination or is it going to be a Hofmann elimination? So OCH3, is it going to be a small base or a bulky base? I gave you the things to watch out for. So what two functional groups did I tell you to watch out for if it was a bulky base? If in the name you have tert butyl or isopropyl, if you have either of those names in there, it is going to be a bulky base. All right, there are a few other bases that can sneak through, but for right now, until I take a look at your practice exam, just remember this. So sodium methoxide, bulky base or small base? Max.
Small.
It's a small base because it doesn't have a tert butyl group. This is one of our small bases. Remember, you're always going to automatically default to small bases unless it has tert butyl or isopropyl in there. Just assume that it is. So now I'm going to color these. My double bond is going to form between which carbons? The red one for my major, the purple one, or the green one? Where is my double bond going to form between my alpha carbon and which one of those for my major product?
I want to say the purple one since
Yep.
the other ones have 3 hydrogens.
Correct, right? So that's a good way to tell that. So our major product is going to form here like that. Our double bond is going to form between the more substituted carbon and the carbon with the leaving group. This is our major. Our minor is going to be the other one. And it doesn't matter because you're going to get the same thing. So you're going to have a double bond like here or, oh, that was weird. You're going to have a double bond like here, or you can have it on the other one. But this is going to be your minor product because your Zaitsev product is always preferred when you have a small base. So Matthew, if I wanted the reaction to favor a Hofmann, what type of base could I use?
A bulky base.
Yep. So what would be an example one though, Matthew, of that? What's a base?
Tert butyl or isopropyl.
Tert butoxide would be one. Lithium diisopropylamide, LDA, common bases. But as we go through your exam, I'll point out and make sure I highlight, like, yes, this is clearly a bulky base. This is a small base. But does this make sense when you look at this now and say, I look at my reagent over the arrow, I take a look at, is it elimination, is it substitution? Like I figure out I have a strong base nucleophile, and then I look at the carbon that tells me specifically what's going to happen. And so then I just do all of these things.
Makes
How you
much more
guys,
sense.
how you guys feeling about that?
A lot better than I was.
Yeah. Like
Okay.
I understand major and minor now.
Yeah.
So the way to think about this is the reason why, do you want this, the real truth about these reactions is that when we do these reactions in lab, no one ever does these because they're so unpredictable because you have major and minor products. You want reactions that only give you one product. So essentially you just have to kind of figure out what's going to be preferred. So you can have multiple products form, but if you pay attention to like the basic rules that we put forth, it'll all kind of be like, okay, I know that it has to follow this rule, I has to follow that. So I'm gonna pause this real quick.